Okay, you can hear me. Home stretch. This is a microacoustic chamber, not in competition with the one that's coming in any way, scale particularly. So right now, your current options for physical testing are the ASTM laboratory testing that Judith just mentioned, or an as-built field test. There's ASTM criteria for that. And we saw potential for a conceptual and iterative testing on a much smaller scale, quicker, that would happen before you would send your test off to an ASTM lab. Also using it for prototyping at much lower cost. Big panels are being tested in these ASTM labs and the associated assembly materials to go along with it. And then demonstration both for students, but also potentially your clients for acoustic principles, assembly performance, really comparative benefit to seeing those, hearing those actually. This morning session mentioned some of the previous acoustic testing we did at ASTM labs, and in that process, we had to cull our ideal set of assemblies down quite a bit, and shipping panels to the Chicago area for that testing, waiting 28 days for concrete topper to cure in the test chamber itself. We saw the potential for doing something on a smaller scale and closer to home. So our design for the chamber starts with eliminating the source room. So you have a source and a receiving room. The source room in our case is whatever room the microacoustic test chamber is in. We reduced the microphone array to a single microphone from either a fixed set of microphones or a microphone on a boom that swings around continuously. And then we had to figure out how big is just small enough. So we're a half a wavelength from the test sample itself and a quarter wavelength from the interior volume of the test chamber. And that geometry puts us able to test down to a frequency of 250 hertz. So the green line is where we sit among ASTM tests in blue. And that's at a half a cubic meter interior volume, whereas a new test chamber today, both source and receiving room are recommended to be over 200 cubic meters. So we're doing a lot, we think, with a little space. So here's our assembly. It's made of 1-inch ply with a noise-proofing compound in between, unistrut holding it all together, an inner and outer box, and sand filling that as both mass and also the voids in the sand make it a really great acoustic dampening material. So we can work with a sample size that's 32 by 32 inches and able to be lifted by two of us into the chamber, an adjustable and maximum sample depth of 12 inches, including acoustic treatments. And here's a section of that. The sample is adjustable in height, you can see on the top, so you can use ceiling mounted or floor mounted acoustic treatments. Some construction assembly, the noise proofing compound on the left, foam tape to keep the sand in. This is completely disassemblable, and we actually put it together in a van on our way down to Mass Timber Academy, where it was able to be forklifted out of the van in the rain. You may have seen a version of an acoustic demonstration at Mass Timber Academy. Let's see. It's currently assembled in our Portland lab in the White Stag building. And this is a little bit shorter than it took to actually do, but there's over a yard of sand that's in there. And those benches on the side allow us to move a test panel into place and then get up on the benches, lift it into the chamber, and also do what we need to do to finish the test sample in there. Next steps are validating and calibrating the chamber against those ASTM tests that we did. Our acoustic equipment actually just got back from Europe and made it through customs this morning. So we're really excited to get going on that. The omnidirectional speaker there in the left kind of was concerning to customs. It looks scary. And we're also excited to test some ideas that we have and sample prototypes we've created. So doweled cross laminated timber has the inherent property of not using the interstitial space between lamella for bonding, and that is potentially an area where acoustic treatment can be applied. So cork in this case, and also kerfs in between lamella as well for additional air spaces. So we have this ready to test as soon as that equipment's ready to go. We've also been working on the recipe for some mycelium acoustic panels using Nike Grind as a project through our industry consortium. And we intend to test some mycelium in the acoustic box as well. And mycelium is my segue to another project on microbes. Wood species, surface coatings, and relative humidity, and their impacts on microbial community structure on mass timber. This is a joint U of O and OSU project. Kevin Vandermeer-Melberg and Gerald Presley leading the research. And we're currently processing those microbial samples and doing metagenomic sequencing on those. So interior exposed wood has a biophilic property and elicits positive emotional response, but it also has physiologic impact on human health. And we're looking at a couple of those pathways that may be responsible for some of that, including improving indoor microbiome, which we contribute to, and also wood might as well, does as well. And relative humidity and its buffering potential. Most building types don't have active humidity control, and wood may be a passive way to do that, again, for human immune system health. So wood is a porous surface. It fosters beneficial microbes as well as some of the detrimental ones, potentially harboring detrimental ones we saw earlier. And it also has, some species have the potential to inactivate pathogens through antimicrobial benefits. So we're looking at Doug fir larch and spruce pine fir sourced from bog and timbers, 3-lam CLT, and these are our wood cookie test samples to go in microcosms as cut in Emerson. So the wood can buffer indoor humidity, and I guess for time, the punchline is that mass timber should have both a short and long-term buffering potential. What these plots show is that the surface is really responsible for short-term buffering. This is a 24-hour scale, and if you stretch this out, those deeper fibers with slower diffusion rates are responsible for longer buffering potential there. So we should have both daily and seasonal influence potential from exposed wood in buildings. Our microcosm experiment is split into a regime of 20% relative humidity and 60% to kind of get at differences between those. Coatings obviously are used for durability mostly, and they can affect the last two things I just mentioned. So we're interested in maintaining those health benefits of wood, and also the coatings may potentially be able to add antimicrobial functionality through their formulation. We're using the 3 coatings shown here, Stenson, Osmo, and Timber Pro, in addition to unfinished samples. Constructing our microcosms and putting them in our mirrored box artificial sky, we're giving these microcosms a daily dose of 12 hours on, 12 hours off, even electric light. You can see the glass skylight there in every microcosm. They're 50-liter stainless steel microcosms. And then using our climate chamber and the HVAC equipment associated with that on the right to condition the air that's delivered to those microcosms. Here are our samples in addition to some stainless steel control plates before they went in the microcosms, coated with those 3 different coatings. And we inoculated them with household vacuum dust, homogenized and sifted. We got most of the dog hair out. And these were brushed off and knocked off before they went in. So they weren't loaded to this degree, but we've used this inoculum in the past, and it's a real world, whole sort of microbiome instead of picking just a few microbes and putting all your eggs in that basket. So here are those microcosms. Air is drawn through the microcosm with vacuum pumps, and as it exits the chamber, it's pulled through a 0.2 micron filter paper, and that is used for our air sampling. So we're interested both in surface microbiome, but also what it may contribute to the air microbiome for each of those microcosms. So on the right is that filter paper sample, and periodically throughout a 6-month runtime, we're sampling the surface of those with swabs. At the end of that 6-month period, we quartered off each sample and tested cleaning products, including common healthcare used cleaning products. And at this point, those seasoned samples went to Jerry's lab, as well as some freshly coated samples and the raw coatings themselves. And he's looking at, he's taking a destructive sample from the surface that includes both the coating and the subsurface wood material to get at the interaction and absorption of microbes into the wood surface, and grinding that up into a wood powder, oven baking it. And that's the starting sample for an inoculum study to look at antimicrobial functionality on these wood surfaces. Wood cookies also went to a parking lot in Eugene, to a 28 cubic meter modular unit that we had there. We were doing COVID testing near the COVID dorm, and also nebulizing surrogates into this space. So on the left, you'll see our nebulizers. What we did was nebulize MS2, which is a bacteriophage and the viral surrogate, as well as a bacteria, Staphylococcus epidermis, into the room for 30 minutes. We had, it's hard to see probably, but sterile Petri dishes on each wood cookie, as well as just a location on the wood cookie to then swab. And we took right after the nebulization period, took a swab, and 6 hours later, took another swab. And we hope to see whether there's any effect on viability of those two microbes in the future. That's what I've got today. Thanks.